Hi, everyone. This is Dr. Tsai, and here we're going to start the first chapter of this CHEM 101. And I have the note provided with you, so you can use the note while watching the video, and also you can make your personal note while you're studying the chapters. There are some reading materials and also extra note in the note area of this PowerPoint handout as well. So let's get started for chapter 1. Chapter 1, we're going to study the basic concepts of matter. So basically introduce you the most fundamental concepts of chemistry. And because chemistry is the study of matter. Okay, so first let's take a look at this guideline of this chapter. This is how basically our chapter is arranged, divided by these sections, and we're going to cover every single one of them. And that's also your study guidelines, because these are basically the section head titles for the content of this whole chapter. Like we said, chemistry is the study of matter. So first thing we want to know is, what is matter? Okay, matter is anything that has mass and occupies space or volume. Okay, mass means how much the amount of something in the substance, in the matter. And space means the volume of the matter. So basically anything that occupies, has some amount and also occupies space, is classified as matter, which is in the scope of chemistry study. Now, of course, matter includes naturally occurring living things or non-living things, or even synthetic materials, anything from small to big. Okay, examples of the matters, for example, give you a more conceptual idea of what matters are, include plants, soil, rocks, dust, air, bacteria, plastics, everything around us, basically. But there are something that are not within the scope of matter, because they don't, we assume they don't possess mass or occupy space, such as heat, light, and electricity. Those are considered to be energy instead of matter. Okay, so this is the definition of matter, which again is what chemistry is studying or is talking about. Now, first, let's take a look at the classification of matter. Matter can be classified based on the physical state. Okay, we have 3 physical states: solid, liquid, and gas. So matters exist in these 3 physical states. But of course, aside from the joke, the 3 physical states have their difference regarding their volume and shape. Okay, for example, as shown in this picture, a solid state has a definite volume and also a definite shape, right? Like the quarter, it has a definite volume and shape. But on the other hand, liquid, it does have a definite volume, which is the volume measured by the container, but it does not have a definite shape. It has an indefinite shape, because liquid is free flow. It would take the shape of the container. So liquid has indefinite shape, but a definite volume. Now, the last one, the gas, which is also different from the previous 2 physical states, is gas does not have definite volume or definite shape. In another word, gas has indefinite shape and also indefinite volume, because once you open up the container, gas will start to come out of the container. So if you put a container capped, the gas will assume the shape and volume of the container. But once you open the cap, the gas will come out as well. So gas has indefinite shape and indefinite volume. So these are the 3 different physical states regarding their shape and volume. Of course, we're going to study more about the differences between liquid and gas and solid in later chapters when we study the physical states. But if you think about the state of matter, actually depends on a few things. Okay, for example, the first thing is the strength of the forces holding the particles together. Okay, in a certain state, if the particles are held together tight, So you will mostly expect the matter to be a solid state. If the particles are held far away, like loosely held, then particles tend to go away from each other. So they will mostly expect gas state. Of course, something between is the liquid state. So that's how the nature of the substances particles holding together determine the physical state. And of course, temperature also has effect on the physical state of a matter. For example, higher temperature, the particles tend to break apart. So higher temperature will mostly result in a liquid or gas state. Lower temperature, the particles tend to stay close. So you will expect a solid state. And finally, a pressure will also affect the physical state for some substances. Usually lower pressure, the particles tend to separate, or especially on gases, lower pressure, then the particles tend to like a spread. So you will mostly expect a gas state. Higher pressure, if you compress the molecules together, the molecule will be held together tighter. So you'll mostly expect a liquid or solid state. For example, our propane gas you guys use for barbecuing is stored as a liquid in a high pressure tank, right? When you release the pressure, lowering the pressure, the gas will can actually come out. So higher pressure in the tank, the state is liquid. You can shake the tank as you can hear liquid. But when you open the valve, the pressure is lowered, the gas is going to evaporate and escape from the tank. Okay. Next. Okay, when we study matter, we want to know their properties. Okay, when we talk about properties of matter, we have to classify into two types. One type of property is observed, okay, observed without changing the identity of the substance. Okay, if the property is observed without changing the identity of the substance, we call that property, or call those properties physical property. Means in these properties, we will observe these properties, the identity of the substance don't change. And the physical properties mainly include the color, the odor, the physical state, liquid, solid, and gas, or the melting point, boiling point, basically what temperature do they melt and boil, and also how hard these substances are. So these are some general physical properties. Again, when we observe these properties, for example, when we observe something boiling, the basic identity of the substance does not change. On the other hand, if a property is observed during the change of identity, for example, like we say here, if the property is observed when the substance undergoes or resists change to form a new substance, means the identity is changed. If that's the case, we call the property chemical property. Okay, normally flammability, toxicity, or corrosiveness, these are chemical properties because these properties are observed when the substance undergoes a change of identity. For example, flammability. When some substance undergo flame, like a burst into flame, like a burning, then most likely the substance is converted to a different substance or a few different substances. And toxicity, the same. The substance has to interact with some biomolecules in our system, then the molecule will change its identity as well. So chemical properties involve the change of identity, physical property, without changing the identity into new substance. Okay, so here is a few quick concept check. For example, this picture shows you the Statue of Liberty. You guys know the Statue of Liberty is made of copper, but we know copper color is more like a purplish bronze, purple, yellowish color. But now we know the Statue of Liberty is green. The reason is that the Statue of Liberty is actually undergoes oxidation reaction when it is in contact with air and oxygen in the air. So moisture and oxygen in the air. And because of that, the copper of Statue of Liberty actually changed to a different substance. That's why it turns different color, green. And I have a link here under this note. You can study more about the story of Statue of Liberty color. But again, this property is the chemical property of copper because it is actually corroded or corroded, patinaed by air and moisture in the air. Okay. The next question is, to measure the boiling point of a substance, a liquid must be changed into a gas. But the question asks you, why boiling point? Again, boiling point is the temperature at which the solid and the liquid becomes gas. So why boiling point is considered a physical property when the gas appearance is much different from that of liquid. Okay, even though gas looks different, the appearance of gas is totally different from a liquid, but when something boils, what happened is the molecules become separated. Okay, the molecule identity itself does not change. Only when the molecule change from liquid to gas, the distance of the molecule are bigger, and also the molecules are more separated, and molecule has lighter interactions, but the molecules themselves, the identity remain the same. So boiling point or the boiling process is a physical property of matter. Okay, and here is another statement. I hope you can use that to practice. And I have the answer key here left in the notes. I want you to use that as some concept check to see if you understand these concepts, especially the properties of matter. And here is another practice. Again, the answer key is provided in the note area, so you can use that to practice whether you understand it correctly about physical and chemical properties. Okay, after that, let's take a look at a very similar concept. When we study matter, matter have properties, and also matter will undergo changes. So sometimes a change will only involve the physical appearance, but not the identity, not the chemical composition. Then we call those changes physical change, very similar to physical properties, because those changes don't change the identity, don't change the chemical composition. So those type of change we call physical change. Examples of physical change, for example, like we just said, boiling, right? From liquid to gas. It only changed the appearance. Liquid is different from the appearance of a gas, but the identity of the substance is the same. The molecules just become more separated. Or another way is melting, right? If solid becomes liquid, like ice liquid melts into water. And that's also a physical change, because during the change, water molecules remain the same. The only difference is the water molecules are very nicely organized in solid, and now it's not that organized in liquid forms. So that's the difference during, or what happened during the change. And another example, for example, I have a piece of paper. Okay, I have a piece of paper. If I tear that piece of paper apart, right, that change is or tear into a smaller piece, and that change is also called a physical change, because paper identity, the chemical composition of the paper does not change. It only becomes smaller or divided. So these are some examples of physical change. Again, physical change does not involve the change of the identity or the chemical composition. Okay, another change that is similar to the previous concept as well is called chemical change. In chemical change, the difference is during and after, or before and after the change, the chemical composition of the substance is changed, or we say the identity of the substance changed. What does it mean for identity change? It means the substance changes into a new substance. So the process of chemical change involves the formation of new substance, either one new substance or more new substances. If that's the case, we call the change chemical change. Just like we said, the Statue of Liberty turns green. The reason it turns green because copper, this metal, turns into copper oxide, which is in green color. So copper oxide is a different substance than copper. And another example, for example, if you light on a match, right, the some phosphorus, some explosive on the match tip, you can search more what are on the match tip. Mostly is phosphorus containing compounds. After the burn, right, they burn into different substances. The tip of the match will no longer be urgent. Or if the wood stick of the match keep burning, the wood, which is mainly cellulose, will become right, mostly inorganic salt like ashes. So these are examples of chemical changes. Again, remember the difference between chemical and physical is you want to ask the question, does this change involve the changing of the identity or composition of the substance, or does it involve the generation or formation of new substance? If it does, chemical. If it doesn't, physical. Okay. So here's one quick practice. Which one of the following is an example of chemical change? We said before, chemical change, you need to involve what? The change of identity, change of composition, and change of or getting new substance. So the only one that is a chemical change is burning a wood. Remember, I said burning a wood. Wood is made of cellulose, and burning a wood left ashes are basically inorganic salts or some carbon residues, etc. But chemical change basically change the composition of wood, chemical composition wood. The other ones are all physical change, such as crushing a rock salt, you just divide in smaller pieces, dissolving sugar in water, sugar is still sugar, water is still water, they're just mixed together, melting a popsicle, melting is that change from solid to liquid. It is still popsicle substances. You're not getting new substance. So the only thing that getting new substance is burning the wood. In fact, you can take a short note here. Most process involve burning, flame, right? Heat, flame, sound. Those processes are most likely chemical process because heat, flame, sound are actually signs of chemical changes. All right. Next is a very quick and actually another practice, but this practice involves me to give you some more background of it. And this is basically an experiment asking, hey, if I apply electric current to 50 mL of water, okay, 50 mL of water, and after that, nothing is left in the container of the 50, means the 50 ml of water is gone. It's changed to something else by the electric current. They ask you what actually happened. Okay, this one I need to give you some background showing this is what the experiment is talking about. You can see that I apply some electric current using 9-volt battery. I use 2 wires and put them into a beaker. Assume we have 50 ml of water. And after that, you will see that after the connection connected, you will see that the water start bubbling, right? You will see some gas start to accumulate in test tubes on these 2 electrodes. Okay, and also you will notice that one of the gas will be approximately, or actually it's accurately two times the volume of another gas. Okay, this is happening. This process is called electrolysis. Okay, basically what happened is electric current supply the energy to split water. They split water into the elements of water. We know water, everybody knows that water is H2O, right? Water is made of with hydrogen and oxygen element combined together. But with the help of electricity, the element of water got split into 2 elements, hydrogen and oxygen gas. And in this process, the volume of hydrogen will be twice as much as oxygen. We'll learn that in later chapters as well. That's why you collect more here. Basically, this test tube is hydrogen, and the one less here is oxygen. So this is what happened in experiment. Of course, we know that because water is basically split into hydrogen and oxygen gas, water is no longer water. So from here, we know that this process is basically a chemical change. Okay, so we're looking at C and D because it's chemical change. We're getting new substance. And let's take a look. See, a chemical change takes place converting water into its elements, hydrogen and oxygen. No residues left because water is a pure compound, which is the case. Again, we'll study all these, some more terms in later on, but I want to show you this is what's happening inside the tube, inside the test tubes. Water is basically split into elements, okay, into elements. D is wrong because water is not converted into gas per se, but water is basically split into the elements of water. Okay, answer is C. Okay, answer is C. Okay, after that, you can take a short break. Let's continue. A very important concept is the classification of matter by composition. We don't matter. We basically study Okay, we basically study everything, right? Everything around us, including small things, big things, living things, synthetic things. We basically study almost everything around us. So in order to study the matter, we have to have a good way of classifying them into categories so that we can better study these matters. So one way to classify the matter is to classify matter by composition, how they are composed, right? So the first big category of classification by composition is matter is classified into two big types. One type, we call it pure substance. Another type, we call it mixture. Okay, pure substance versus mixture. Now, pure substance means this matter only contains one single substance. It's pure, nothing else, just one single substance. We call that pure substance. Very easy to understand. Now, mixture, probably now we know that mixture is basically more than one pure substance combined together. Of course, the definition is physical combination of two or more substances. The reason they call the word physical is when you combine two or more substances to make a mixture, you make sure these two or more substances don't interact with each other chemically. That means you don't generate new substance. You're simply combining them together. But the substance themselves don't change during the combination process. The substances themselves don't change their identity during the combination. They're just physically combined, coexist together. So that's why we call it physical combination, because you're not resulting in new substances, because we're not talking about a chemical reaction. So if you have two or more substances physically combined together, we call that a mixture. Okay, mixture, single substance, pure substance. Two or more substances physically can be combined together, a mixture. Now, first, let's take a look at mixture. Of course, we're going to focus on pure substance later, but first, let's take a look at mixture. Mixture can also be further divided into two types. Okay, one type is called homogeneous mixture. Another type is called heterogeneous mixture. Okay, the two words are different by the prefix homo and hetero. Okay, homogeneous means the mixture is one single visible phase. Uniform, okay, uniform throughout the whole mixture, one single visible phase. Another mixture is called heterogeneous mixture, means you see various different phases, okay, various phases. What does the phase mean? I'll give you an example. You can very easy to understand what these two terms mean. We know perfume is a mixture, right? Perfume has water, has a ton of them. But when you look at the bottom perfume, the whole thing is uniform, right? One single phase uniform. So if that's the case, we call perfume a homogeneous mixture. Now, imagine if you pour some oil in water. We know during our basic life experience, oil pouring in water, they're going to separate. But oil and water, they're mixing together. So we call the oil and water mixture, right? But when you look at the oil mixture, what you see is a separation of two phases. Okay, top phase is oil, bottom phase is water. You can even pour some sand in it. Say three phases, sand will be in the very bottom. So if that's the case, oil, water, or oil, water, sand is two or more visible phase mixture. We call that heterogeneous mixture. So based on the appearance of the mixture, we can further classify into homogeneous mixture and heterogeneous mixture. Okay, so here are examples. Okay, heterogeneous means many variable phases like oil and water, sand, water, and mud. Mud can be top, can be wet, bottom can be more, top can be dry, bottom can be more wet. So you can see it's not uniform. But homogeneous mixture like your tea, perfume, Gatorade, these are the same throughout the mixture, is uniform throughout the mixture. So we call that homogeneous mixture. Okay. So quick concept check, which of the following is a homogeneous mixture? Remember, homogeneous means the whole thing has to be what? Has to be uniform. Which one is uniform? Gasoline is uniform because when you pour gasoline into glass, you will see it as a whole uniform mixture. But gasoline is not pure. Gasoline is uniform. It's mixture. The reason we know it's a mixture, of course, even though you don't want to know what gasoline is, but we know gasoline on your label of the fuel pump, you see that contains up to 10% of ethanol. So you know that gasoline at least contains what? ethanol in it, or gasoline nowadays. So because of the mixture of gasoline and ethanol, you know it is a mixture, but gasoline is a uniform mixture. So one of the answers with uniform mixture is gasoline, which is homogeneous mixture. Okay, other ones are not homogeneous mixture. Pure water is a pure substance. Jelly beans is heterogeneous, right? Because jelly bean, the color is not really uniformly distributed. Soil, we have tons of things here and there. Topsoil may be dry, bottom soil may be wet, is not homogeneous. Copper metal is a pure substance, again, not a mixture. So the only homogeneous mixture is gasoline. Okay, and here is another concept check. I want you to use that as a practice. Again, the answer key is provided in the note. See if you understand the concept of classifying matter into pure substance and mixture well. Again, remember, pure substance is one single substance. Mixture is physical combination of two or more substances. Okay, next is more important. Okay, more important is how do we classify pure substance? And like you said, pure substance is one single substance, but the one single substances can be further classified into two types as well. One type is this substance only contains one element. Okay, one element, such as copper, such as oxygen, such as nitrogen. You can see that sodium, you can see that this substance only contains one element each. If that's the case, these substances cannot be further broken down chemically into simpler substances, or simply chemical means simply chemical or physical means they cannot be further broken down. They're just single substances already. If that's the case, we call those substances elements. The elements, they only have one element. That's why they cannot be broken down into simpler substance. We call those elements. Now, another type of substance, pure substance again, is they're made by two or more elements, okay, combined together, like calcium oxide. Carbon monoxide is made by carbon and oxygen. Calcium oxide is made by calcium and oxygen. Sodium hydroxide, chloride is made by sodium and chlorine. And glucose is made by carbon, hydrogen, and oxygen, etc. So these substances, they're pure, but they're made of two or more elements combined together. Okay, these substances, because of that fact, they're made by two or more elements combined together, they can be further broken down into their constituent elements by chemical means. Okay, by chemical, because they have multiple elements combined, they can be broken down into elements. Just remember, like water, right? Water, we can split water into hydrogen and oxygen elements. And because of that fact, these pure substances with two or more elements combined, we call those compounds. Okay, compounds. So what's the difference between element and compound? Element, you only have one element. Compound, you have two or more elements combined in the structure, okay, in the substance. And of course, the basic definition will be element. Because of the only one element, they cannot be further broken down into simpler substance. Compound, because they have two or more elements, they can be they can be further broken down into their constituent elements by chemical means. Okay, by chemical means. And one thing I want to point out, maybe some of you even don't have that confusion, you can even skip this, but some of you may confuse between these two terms, compounds versus mixture, right? First, you have to know is the bottom line is these two terms are totally two different types of classification. Compound belongs to what? Belongs to mixture, means what? Compound belongs to pure substance, means what? Compound is a pure substance, one single substance. While mixture, even though it has two or more components mixing together, but it's no longer pure. So these are totally two different classes. Okay, compound, again, even though they're made by two or more different elements, after they combined, these substances are pure. Each compound is a pure substance. But mixture, okay, mixture is two or more substances combined together. It's not pure substance. So that's the bottom line. Okay, another one, okay, which if we dig deeper, what's the difference is compound, because it is pure, Okay, because pure, you cannot separate the element by physical means. Okay, you have to use chemical means. But mixture, because they're physically combined together. Okay, you can separate the components by physical means. Okay, what does it mean? For example, if you think about sand and water, right? Sand and water is a mixture, but these two components of the mixture, sand and water, they're actually just physically combined. They're just putting sand in water. And we can separate the sand and water by simple filtration. If you have a filter paper, you can filter off the sand off the water. So you can separate sand and water, right? And that's not even doing chemical reaction. It's just physical means. So mixture components, they can be separated by physical means because they're mixture, two or more components combined together. Compounds, you cannot separate because it is already pure. You cannot break down with physical means. You can break down compound by chemical means. So that's the deeper difference. But again, some of you may be confused with these two terms. Just remember, compound is a pure substance. It's not a mixture. Okay, this is one quick concept check asking the difference between an element and a compound is I think the answer is D, right? The element cannot be broken down into simpler substances by chemical means, or a compound can be broken down by simpler substance by chemical means. Okay, remember chemical means. Okay, now after we study these classifications, pure substances, elements, pure substance can be classified into pure substances and mixture. Pure substance can be classified into mixed elements in a compound. Mixture can be classified into homogeneous mixture and heterogeneous mixture. So after we study all these, how do we classify a matter? If I give you something, here are 3 standard questions to ask. Okay, one question is, first of all, does this substance contain 2 or more different substances present? If it is one single substance, pure substance. If there are 2 or more different substances combined, mixture. So ask you the question, does this substance contains 2 or more components, okay, present? Then you can know whether it is a pure or mixture. Now, after that, you answer each one of these two, either one of these 2 questions. If it is a mixture, does the sample look uniform? If it is uniform mixture, homogeneous. If it is not uniform with layers, with phases, heterogeneous mixture. Now, if it is a pure substance, ask yourself, does this pure substance contain one single element or 2 or more elements combined together? If it is single element, it is an element. If it is 2 or more elements combined, it is what? A compound. So basically, whether the pure substance can be broken down into simpler ones chemically. If it can, compound. If it cannot, element. Okay, so these are some questions to be asked when you're classifying a substance. So here, a picture showing you the difference between these 2 types. Kind of, again, you can cover the answer key and even try this by yourself. This picture shows you different types of matter. Okay, the first one, you can see that all the same. One type of element, okay, one element present, the red ball, right, is the element, one of them. There's nothing else present. So we know this is a pure substance and an element, okay, which is similar to the second picture. You can see that even though they're made by 2 atoms together, okay, 2 together, but they're the same. Okay, one element present in the structure, in the formula. So one element present means what? It's an element. Balls or double balls, they look the same. So both the first one, the second picture, they're pure substance, right? Because they are only one type or one single substance present. Okay, the third picture, you can see all these molecules look the same. So we know that's a pure substance. Okay, if it is a pure substance, means either element or compound. And we know that each molecule is made by 2 elements. You can see that one is purple and another one is green. So 2 elements made the molecule. We know it is a compound. Okay, compound, it can be split by chemical means. Okay, last picture, you can see these substances are mixed together. Okay, we have element, we have this element, we have that element, we have this compound, they're mixing together. So we know it is a what? It's a mixture. So this is the picture, visualized way of telling you, hey, what these, or how do we classify, or how do we understand the concept of pure substance versus mixture, element versus compound. Okay, and this is another practice asking you to choose substance X, Y, Z, and T. Okay, classify these substance based on the picture. And how do you classify? And the first one, you can see that you have two substances, two types of molecules mixing together, right? One of it is here, another one is here. So they're different. So this is what? This is a mixture. Okay, X is a mixture. Y, you can see that you also have two types of molecules mixed together, right? Two different molecules mixing together in the whole combination picture. So we know it is also a mixture. Okay, number three, substance Z, you can see all the molecules look the same, and there's one element present. So this is an element. Okay, last one, substance B, you can see all molecules the same. So it is a pure substance, but each pure substance has two elements together. So we know it is a compound. Okay, compound. Key is a compound. So these are the classification of these four substances. Okay, next, after we study the classification of matter, let's take a look at the elements. Okay, the elements. Now, in our periodic table of elements, even though no matter you have seen the periodic table or not, we're going to use this a lot in this class, of course. But if you look in the periodic table, you will see that there are 118 known elements in our periodic table. Okay, in our periodic table, and also we have a link here. Okay, I want you to use that link. Okay, stop the video or pause the video and use the link to take a look at these elements. Okay, take a look at this element first by yourself and see if you can figure out how many elements out of the 118 occur naturally and how many elements are actually synthesized in physicist labs. Okay, here, of course, the answer, I found it for you already. In our modern periodic table, out of 118 elements, there are 92 naturally occurring ones, okay, naturally occurring ones found in Earth, crust, and ocean. Of course, those are in green. Okay, those are in green. And two elements, okay, those are in orange color ones. Okay, this one, okay, this one, and this one. Okay, TC and PM. These two, technetium and promethium. These two elements are created as byproducts of nuclear reactors, okay, like nuclear power plant as byproduct. So these are assumed as naturally occurring. Okay, this is naturally occurring. The other ones in purple, okay, are actually synthesized by like a particle reactions, particles smacking these other elements. And these elements in purple normally have a short lifetime. Okay, they work at half-time, they're very short. Okay, they're not considered naturally occurring. So this is the periodic table showing you most of the elements we can find in our Earth, crust, and ocean, but some of them are actually synthesized in the labs. They have a short amount of time of being detected. Okay, being detected. And also we can take a look at the presence of the elements in different entities, okay, like in our universe, for example, in this pie chart showing the abundance of elements in atom percentage in the universe. You can see that our universe is mostly made of what? Small elements, small atoms. Okay, most of the elements present, 91%, is in the form of hydrogen, and 9% is in the form of the helium. This is actually the first two elements in our periodic table, and that tells you what universe started with smaller ones and build up more complex ones, right? And even including our body, our Earth, they're actually built on small elements like hydrogen and helium. And as a matter of fact, our sun in our solar system, the sun in our solar system is actually a big fireball, right? They're emitting energies, but the fuel of that is basically hydrogen and helium. They're doing a fusion reactions. Okay, that's why our universe is filled in these small atoms, hydrogen and helium. Now, if you take a look at the Earth crust, okay, if you look at the universe, we take a look at Earth crust, you'll find the percentage, and you have more variety of elements, more complex ones, not just smaller hydrogen and helium now, because we're a planet. Okay, you will find out the most abundant element in our Earth crust is silicon and oxygen. Okay, the reason is our Earth crust, especially surface of the Earth, is made of rocks, sand, and dirt. Okay, the main component of these structures are silicate. Okay, they're basically silicon oxide salt, like salts. Okay, silicate. So that's why we have a lot of silicon and oxygen in the Earth crust. Okay, because Earth said rocks, sand, they're mostly, especially sand, they're mostly silicates. Okay, and finally, if you look at our biological system, like in a human body, okay, we are made of a lot of elements as well, but the most abundant elements are hydrogen, oxygen, followed by carbon. Okay, for hydrogen and oxygen, the reason we have a huge abundance of them, because again, human body is 70% of water. So apparently we have a huge abundance of hydrogen and oxygen. But if we get rid of water, okay, get rid of the hydrogen and oxygen, the most abundant element constructing a human body without water is carbon. Okay, we're actually carbon-based. Okay, carbon-based living organism. The whole planet Earth is carbon-based organism. Organic chemistry, okay, if you get a chance later on to study, is actually the study of carbons. Okay, so here is the chart showing you the composition of a human body. Okay, we can explain why we have a different abundance of different elements at different places. Okay, places. Now, when we study elements, of course, when we look at a periodic table, study elements, we first need to know how do we write or name these elements? How do we note these elements? So here I'm showing you the chemical symbols and names for these elements. Okay, first is the symbol. Okay, because that's the one we use most of the time when we study chemistry. We use chemical symbols, the element symbols, to represent, to tell people the elements. Okay, a symbol of an element is either a single letter or a two-letter symbol. If it is a single letter, the letter must be capitalized. If it is a two-letter, okay, it is always a capitalized letter followed by a lowercase. That means the first letter for a two-letter symbol, the first letter is capitalized and the second is not capitalized. So from now on, because you're studying chemistry, when you write a symbol, make sure you write it correctly. Do not use a symbol with two lowercase letter or with a symbol with two capital letter. If you have two capital letter, you're talking about two elements, not one element, because element can either be one capital letter or a two-letter, a capitalized followed by a what? Followed by a lowercase. So because again, you're studying chemistry, don't make those low mistakes, because we have to be strict on the symbols. Okay, and after you know what the symbol looks like, and here shows you some examples of the symbol. You can see symbols, you can see carbon, nitrogen, phosphorus, argon, lithium, silver, gold, iron, lead, and copper. You can see that the symbol can either be single letter or two-letter with a capital followed by lowercase. And then let's take a look at the names briefly. Okay, the name of the elements mostly are derived from the name of the element themselves. The symbol are derived from the name of the element itself. But the name of the elements doesn't have to be in English. Some are from English, such as nitrogen, phosphorus, carbon. They're from English, though the symbol is derived from the name of in English. But some elements, the symbol are derived from the non-English names, such as silver, gold, okay, iron. You can actually find these elements. Some of the elements are derived from their Latin names, for example. Okay, so or sometimes the element symbol are derived from a place, okay, from a state, from a country. So there are all kinds of names, not just the name of the element itself, or not just English themselves. And the symbol are actually derived from different names, okay, different names. Now, after we briefly talk about the symbol, okay, we want to introduce you the basic units of chemistry. Okay, the basic tiny block of chemistry. Okay, we know chemistry is the study of matter, but all these matters around us, they're actually constructed by the smallest building block, and that is called atoms. Okay, atoms are the smallest element, smallest particle of an element can exist and still have the property of the element. So basically, in a word, is atoms are the smallest building block of chemistry, are the smallest particle we're going to study in chemistry. Okay, the change of chemistry is the study of what happened to the atoms. So not only all matters are made of atoms, but also if matter changes to another matter, it is actually the change, or we should say later on, we're going to study the rearrangement of the atoms. Okay, atoms is the smallest building block we can expect. Okay, we can expect in study chemistry. All right, let's get back. Sorry, the interruption. Atoms are not only the smallest building blocks of matters, but again, like I said, when matters undergoes changes, they're basically rearranging the atoms. But again, bottom line is the smallest building block chemistry is talking about is atoms. Okay, atoms. That's the smallest or limit of chemical subdivision. Of course, okay, in chapter 3, we're gonna study atoms do have smaller particles inside them. We were actually learning the anatomy of atoms, how atoms are constructed. But again, when a chemical change is happening, or when we're still in the scope of chemistry, we're talking about how the atoms behaves, because atom is behaving as a whole, is behaving as the smallest entity in the scope of chemistry. Of course, atoms are extremely small. You can see that these two pictures, this picture on the right shows you the picture of a helium atom. I believe I put the link here. The helium atom, you can see that the nucleus and also the gray space are how electrons are moving. And again, the size of an atom is about 1 angstrom. It's basically around 100 picometer. And you can see that you need around 254 million atoms to line together to get 1 inch. Again, it's just going to give an idea how small an atom is, but these are the building blocks for matter. Okay, even including our human beings were made by atoms, were made by carbon atoms, hydrogen atoms, oxygen atoms, nitrogen atoms, phosphorus atoms, and etc. Okay. Next, okay, atoms, like we said, they're the small building blocks, so they're still building more complex, okay, more complex stuff. And the first level when atoms build together, bind together, is to make more complex entity called molecules. Okay, group of 2 or more atoms that function as a unit is called a molecule. And the atoms are now in molecules. Atoms are now actually tightly bound together. Okay, bound to a matter. So a molecule is a single, distinct, intact particle. Okay, you're not separating atoms from molecule unless you're doing by chemical means. But a molecule is now a new chemical entity made by atoms, by 2 or more atoms. Okay, you can see that I put on the picture on the right side. Okay, you can see we're looking at all kinds of molecules. Some molecule have 2 atoms, some molecule has 3 atoms, some molecule has 4 atoms, etc. You even have more atoms, okay, more than 4, 10 or 20 or 12 or 20. There are all kinds of molecules, but they're all constructed by single atoms tightly bound together. Now, because molecules are constructed with different numbers of atoms, so we can actually name those based on the number, or name those molecules based on number. We call atomicity. Okay, atomicity. Basically, what it means is if you have 2 atoms in the molecule, we call the molecule diatomic molecule. Like these 2, hydrogen and oxygen, are both diatomic molecules. Now, if you have 3 atoms in the molecule, we call the molecule a triatomic molecule. If you have 4 atoms in the molecule, we'll call that a tetraatomic molecule. Okay, you can see that carbon monoxide, this is another diatomic. Carbon dioxide is a triatomic, right? And this is methane with 5 atoms. We can call it a pentatonic. Penta is for 5. Of course, if you have more than that, you can simply call it polyatomic because you have more than 5 or 6. It's too many. So based on the number of atoms in the molecule, we can name this atomicity, basically one atom, diatomic, triatomic, tetraatomic, based on the number of atoms. Okay, the concept here is the number of atoms per molecule. Okay, per molecule. But now another way of looking at a molecule is you look at the type of or the kind of atoms in a molecule. If a molecule contains no matter what number, 2, 3, or 4, doesn't matter. But if a molecule has one type of atoms present, okay, only one type means all the atoms in the molecule is the same type because you only have one type of atom present. We call those molecules homoatomic molecules. Okay, homoatomic meaning they only have one type of atom, one kind of atom present. You can see that in this picture shows you chlorine molecule, phosphorus molecule, sulfur molecule. These 3 molecules, they have different numbers, but each one has only one type or one kind of atom present. We call those homoatomic. Okay, and also if you link the concept we studied before, if a substance only have one type of element, one kind of atoms means what? The same kind of atom means one element present. We call those substance elements. Okay, we call those elements. So what does it mean? It means homoatomic molecules with one type of atoms present in the molecule must be elements. They must be elements. You can see that this picture shows you all these diatomic, tetraatomic, or polyatomic elements, okay, are present. These are all molecules. Okay, these are all molecules. And also this picture actually tells you that these are the elements that exist in nature as diatomic or tetraatomic or polyatomic. The other elements actually exist as monoatomic, like copper is just Cu, there's no Cu2. Okay, or mercury is Hg, there's no Hg2, it's just single Hg. So most of the element, like in this gray area, most of the element in our periodic table, they exist as monoatomic. The other ones, like the one in purple, including hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, these elements exist as diatomic molecules. Okay, that's how they exist in nature. And phosphorus, sulfur, and selenium, they exist as polyatomic elements. Okay, so those are the elements shown in this picture are the one existed in more than one number. Okay, more than one number. But again, all these molecules shown here, some exist as diatomic, monoatomic, or polyatomic, but each molecule, again, they only have one kind of atom present. If you have one kind, we know these are called homoatomic molecules, and they are all elements. Okay, they're all elements. In contrast, if a molecule contains more than one kind, like 2 or 3 kinds of atom present, okay, like such as carbon monoxide with 2 kinds of atoms, carbon and oxygen, water with 2 kinds of atoms, hydrogen and oxygen, or hydrogen peroxide with hydrogen and oxygen, or ammonia with nitrogen and hydrogen. So these atoms, these molecules, they contain more than one kinds of atoms. Okay, these all have 2 kinds of atoms, basically. If they have 2 or more kinds of atoms present, regardless of the number, again, we're talking about kinds, then these molecules are called heteroatomic molecules. Okay, all heteroatomic molecules are compounds. The reason is, again, because you have 2 or more compounds, elements bound together, right? If a substance has 2 or more elements bound together, you're talking about a compound. Now, if you look at the molecules, you know what is a compound. Compound is actually a substance containing what? Two or more kinds of atoms. Remember, no matter element or compound, their building blocks are atoms. Okay, so now we can have a better understanding of elements versus compound. Both are made by atoms. Element made by the same type of atoms, same kind of atoms. Compounds made by different kinds of atoms, okay, composed of different kinds of atoms. 2 kinds, 3 kinds, they're all compounds. Okay, they're all compounds. So here is a concept check of what we studied about molecules and atoms. Okay, the first question about this formula. Okay, this formula XEF4. Okay, you can see Xe is a element symbol, right? A capital letter followed by a lowercase letter. And F is a symbol, which only is capital letter. So you have 2 elements, right? 2 elements present. The first question is this molecule a diatomic or triatomic or what atomic? What is the atomicity of this molecule? As you can see that this molecule has 1 Xe, Zion, and also 4 fluorine, because there's a subscript of 4. Later on, we're going to study. Okay, don't worry. And so total number of atoms in this formula, in this molecule, is 5. So we can call this molecule pentaatomic or polyatomic, which is fine as well. And next question, is this molecule homoatomic or heteroatomic? Now, because this molecule contains 2 types of atoms, Zion and fluorine, so we know it is heteroatomic because 2 types. And because it is heteroatomic, contains 2 elements, 2 types of atoms, we know it is a compound, not an element. Okay, not an element. Okay, another quick practice. Which of the following statement is true? Okay, let's read all of them. The smallest particle of an element that can exist and still have the property of an element is an atom. Correct. A group of 2 or more atoms that function as a unit form a molecule. That is right. Molecule is made by a group of atoms tightly bound together. Number C, some classification of molecules are diatomic, homoatomic, heteroatomic. You're right, right? Di, tri, poly, we're talking about the number of atoms. Homo and hetero, we're talking about what? The type of atoms. So keep that in mind. They're 2 separate concepts, but they are all description of a molecule. So all of these statements are correct, are true. So answer is D. Okay, finally, next. Okay, we're almost done for chapter 1. The last topic, I think we're talking about the last topic, is the formula of elements. And of course, when elements make compounds, make molecules, the formula of molecules. And we call those, overall, we call those chemical formulas. Okay, chemical formulas. Now, what is a chemical formula? Chemical formulas mostly, again, we're talking about in a compound or a molecule, because if it is an element, we call that a symbol. But chemical formulas are made up of with chemical symbols. Okay, because compounds are made by elements. Elements can be represented by symbols. So the formula are actually represented using the symbols of the elements. Okay, in a compound, when we want to represent a formula of a compound, we have to show 2 things because of the fact that they're made by elements. They're made by different atoms. One thing is what elements are present. Okay, right? If you have 2 elements, you're going to show the symbol of these 2 elements. You have 3 elements, you're going to show the symbol of the 3 elements, because elements are shown as symbols. So you have to list the symbol of the elements in a compound. That's the first thing for a formula. Number 2 thing is not only you have to list the elements that are present, the symbol of the elements that are present, but also you have to tell people the number of the atoms for each element. Okay, some element present as 1 in the formula, so in the molecule. Some element may present as 2 atoms in the formula. So we have to tell people the number of that element in the compound. How many atoms are in there present using what? Using subscripts. Okay, using subscripts. Okay, I know it's kind of like it just by verbally, it's kind of abstract. If you take a look at the examples, or some of you already have an idea, take a look at the examples, you have a very good idea. How do we draw or how do we write chemical formulas? Okay, for example, everybody knows hydrogen, oxygen, H2O is what? Water. And when you put H2O, it tells you what? It tells you water has two elements, two types of atoms present, hydrogen atom and oxygen atom. It also tells us in each water molecule, it has two hydrogen atom and only one oxygen atom. Because what? Because the subscript of hydrogen is 2, the subscript of oxygen is 1, which is not shown in there in chemical formulas. The same. The second formula, C2H6O. Okay, this is the formula, could be the formula of ethanol. Okay, could be the formula of ethanol. It tells us what? Ethanol is composed of 3 elements, 3 types of atoms, carbon atoms, hydrogen atom, and oxygen atom. But carbon atom, there's 2 in ethanol. And there's 6 hydrogen in ethanol and 1 oxygen in the formula of ethanol. So if you have a molecule of ethanol, there are 2 carbon atoms in it, there's 6 hydrogen atoms in it, and there is what? 1 oxygen atom in it. So we use subscript 2, 6, and 1 to tell the number of atoms of each atom's present. Okay, present. Okay, last molecule, okay, last formula, we don't call it molecule. Later on, we're going to study why I don't call it molecule. Last formula, okay, it has 3 calcium, okay, 3 calcium, and it has 2 PO4. Okay, it has 2 PO4. These 2 PO4 tells us what? These 2 PO4 tells us, or be more specific, these 2 outside the parenthesis tells us there are 2 of what's inside the parenthesis. 2 of what? PO4, because PO4 is inside the parenthesis. 2 of PO4 means 2 of P, 2 of O4. 2 of O4 is what? 8 oxygen. Okay, O4 is 4 oxygen. 2 of O4 is 8 oxygen. So if you look at this formula, it actually tells us, hey, you have 3 calcium atom. Okay, Ca is calcium. You have 2 phosphorus, because 2 of PO4, each PO4 has 1 P. So 2 of PO4, you have 2 P. And you have 2 times 4, 8 oxygen atoms in this formula. Okay, later on, of course, we're going to explain why we put a parenthesis here, okay, when we study later chapters in chapter 5. Okay, don't worry about it. But again, chemical formulas, basically we use symbol of the elements to tell people what atoms are present, and we use subscripts to tell the number of atoms for each element present in that formula or a compound. Okay, in a compound. So here is a practice asking you, hey, for each of the 2 formulas, can you determine how many atoms for each element are present? Okay, we can do it very quick. H2SO4, we have 2 hydrogen atom, 1 sulfur atom, and 4 oxygen atoms. This is the formula of sulfuric acid. Number 2, okay, number 2, this formula, we have 2 iron, 2 Fe, we have 3 of CO3. Remember the 3, this 3 is outside the parenthesis, means 3 of CO3. 3 of CO3 means what? There's 3 carbon, and 3 of O3 means you have 9 oxygen. Okay, 9 oxygen. So 2 iron, 3 carbon, and 9 oxygen atoms present in that particular formula of B. Okay. And finally, okay, I think this is a concept question covering some of the topic in this chapter. I think this is the last page. You were given 2 cylinders, one containing a gas, each containing a gas, so 2 cylinders of gas. You request to test the flammability of each gas, and you discover that one gas is very flammable, but the other gas can extinguish the flame. So they're asking what these 2 gases are. Okay, this is of course like kind of like a wild open type of question. Okay, first one is flammable gas. Okay, we know from our perspective or our daily life perspective, the common flammable gases are either hydrogen, or another one is our natural gas, which is what? CH4, okay, methane. So these two are the flammable gases, okay, the flammable gases. Now, the other gas which extinguish flame, right, was used in fire extinguisher. The gas, some of you may know, some not, that puts off fire, will be CO2. Again, these are, again, some open, but based on our common sense and life experience. So these are some possible answers when we do answer. Okay, now, but most importantly is when we give the formula of these three, the question testing us is not, do you know if some gas is flammable or not flammable? Most importantly is we want to classify these based on the formula, right? Based on the different types of molecule there. For example, if the answer is A, if the two gases are hydrogen and methane, which is not correct, we don't even consider A because one of the gas has to be carbon dioxide. If A, both gases will be flammable, no one will extinguish the fire. So not A. Let's take a look at B. B, hydrogen and carbon dioxide. Makes sense. Okay, hydrogen flammable, carbon dioxide puts up fire. But they ask you, they're classified as respectively. So let's take a look at the classification, which is more important. Hydrogen is a diatomic molecule. Yes, hydrogen is a diatomic molecule, H2. Carbon dioxide is heteroatomic, which correct, because carbon dioxide is made of carbon and oxygen. So it's what? Two types of atoms. So it's heterodiatomic. So answer B is correct. The answer B is correct. Okay, let's take a look at C and D. C, neon and carbon dioxide. Both neon and carbon dioxide, they're not flammable. Okay, neither one is flammable, so we don't consider C. D, hydrogen and oxygen. Okay, hydrogen and oxygen. Hydrogen is flammable, but D, oxygen is not the one that extinguishes fire. Oxygen will actually will make the flame bigger because oxygen is basically one of the required components for burning, for flaming, right? If you want to flame, you want to burn, you need oxygen. So oxygen will make the flame even worse, not extinguish. So answer is B. So we don't need to consider methane. Of course, we are talking about hydrogen and carbon dioxide. Hydrogen is diatomic, carbon dioxide is heteroatomic. Okay, heteroatomic. But again, di-tri, we're talking about number. Hetero or homo, we're talking about what? The type. Okay, the type. So make sure you know the classification of different types of molecules and make sure you know how to draft and understand chemical formula. So far, we're now talking about drafting them. We're looking at first understanding what the formula is and how to use subscript. But most importantly, okay, chapter 1, I know in the future, especially as online class, when you do it on Blackboard, you guys will make some mistakes by not using the correct format. Okay, two things I want to remind you in the end. First is when you write the symbol of the element, make sure, again, either a capital letter or a capital followed by a lowercase. Okay, do not use two capital or two lowercase. Two capital means two elements, not a single element. Two lowercase, there's no such thing. Okay, that's one thing I want to remind you. If you make that mistake, that's wrong because now we're professional chemists, we're looking at chemistry now. Number 2 is, remember, the number of atoms in the formula is indicated by subscripts. So that means when you answer the question in Blackboard, in the answer box, you need to change the number into subscripts in the formula. Do not just use a number like FE2 like this. Okay, do not write like this. You have to change that to a FE, a subscript. Okay, the Blackboard answering box is like a Word document. They have the function of changing something to subscript or even superscript. So make sure you form a good habit. The number in the formula should be in subscript. Okay, I want to remind you because I will deduct points because, again, we're talking about the correct chemical language. All right, that is all for chapter 1, and I'll see you guys in chapter 2. Bye now.